Compound characterization, infrared spectroscopy background. In this webcast, we will discuss the theory behind infrared spectroscopy. At the end of the Introduction to Spectroscopy webcast, we discussed how we needed certain pieces of information in order to identify an unknown compound. This webcast will discuss infrared spectroscopy, which will help us identify what functional groups are present in our molecule. Infrared spectroscopy, as you might guess from the name, uses infrared energy. In an infrared, or IR for short, spectroscopy experiment, you have your IR source, and then the IR source irradiates your sample with a beam of IR light. That IR light is then absorbed by the covalent bonds present in your molecule. The instrument then detects how much of that original energy did not get absorbed. It then plots that data as an expression of Cm to the -1 power. This unit is often called wave numbers, although you may also hear it referred to as reciprocal centimeters or inverse centimeters. The IR spectrum that the instrument produces usually presents the output as percent transmittance. In other words, it shows the data as a measure of how much energy was transmitted through the sample, how much energy was not absorbed. Occasionally, you may see spectra that use percent absorbance instead. What does an IR spectrum look like? Here is the IR spectrum for aspirin, acetylsalicylic acid. Here on the x-axis we have wave number. Here on the y-axis we have percent transmittance. And what we see here are a number of peaks in this spectrum. What do these peaks tell us? We see here that at the top of the y-axis is 100%. What that means is that if this line is close to the top, very little of that light was absorbed. That tells us that there are no bonds in our molecule that absorb the light at this wave number. In contrast, if we look at these peaks here on the right, we see that the molecule absorbed a great deal of the IR energy at these wave numbers. Every single one of these peaks you see corresponds to some kind of bond in our molecule absorbing that light. You will see how this is useful to us as we proceed through this webcast. To begin, let us have a short discussion on covalent bonds. You can treat covalent bonds like a classical vibrating spring. If your bond has a dipole moment, in other words, if your bond is polar, and that dipole moment changes as your bond stretches and contracts like a spring, it is what we call IR active. It will produce a peak in the spectrum. Where that peak appears in the spectrum depends on what wave number of light it absorbs. What wave number of light it absorbs primarily depends on two things: the mass of the atoms in the bond, and the strength of the bond. Now let us talk a little bit more about what I mean when I say a change in dipole moment. Here I have a carbonyl. I have a carbon double bonded to an oxygen, and you know that this bond is polar. In other words, it has a dipole moment, which we represent using the Greek letter mu. Imagine taking that bond and stretching it like a spring. What happens is this dipole moment gets larger. As you stretch the partial positive and partial negative charges away from each other, you get a larger dipole moment. In contrast, if we contract or compress our bond like a spring, we move those partial charges closer together, therefore resulting in a smaller dipole moment. As our bond stretches and contracts, we have a change in dipole moment. If we have a large change in dipole moment, a large delta mu, delta represents change, we would have a strong IR signal. That means we would see a large peak corresponding to this bond in the IR spectrum. It may be tempting to believe that every polar bond can be seen in an IR spectrum. That's not quite true. Here I have carbon dioxide. Carbon dioxide has a carbon-oxygen double bond to the right and a carbon-oxygen double bond to the left. These bonds are polar. Carbon is delta positive, whereas the oxygens are delta negative. Now, recall that being IR active means we see a change in dipole moment. If I take carbon dioxide and I stretch the left oxygen the same way I stretch the right oxygen, in other words, if I use a symmetric stretch, do I see a change in dipole moment? No. These dipole moments would cancel each other out. Therefore, because we would see little, or in this case, no change in dipole moment, we would not see an IR signal. This type of stretch is what we call IR inactive. Does that mean carbon dioxide does not appear in an IR spectrum? It turns out we do see carbon dioxide in an IR spectrum, and here's why. On this slide, you see what we call modes of vibration. These are the various ways bonds in a molecule can vibrate. As we saw on the previous slide, if we take carbon dioxide and we stretch it symmetrically, like you can see here, we would see no change in dipole moment. However, if we take that same molecule, but asymmetrically stretch the bonds, we would see a change in dipole moment, and therefore, we would see carbon dioxide in an IR spectrum. The consequence of having different kinds of vibrations is that one bond can show up in many different places in an IR spectrum. Fortunately for us, we can still interpret large portions of an IR spectrum with ease. Do not memorize these 6 modes of vibration. Simply know that there are many different kinds, and that each kind of vibration can give its own signal in an IR spectrum. To review what we have discussed so far, we know that we can treat covalent bonds in a molecule as if they were springs. In an IR spectroscopy experiment, our compound is exposed to infrared light. The bonds in our molecule absorb some of that light and begin vibrating. These vibrations then give us the signals we see in an IR spectrum. Now we are going to discuss what determines where those signals appear. Let us treat our covalent bonds as springs. I have an atom on the left, an atom on the right, and a bond between them which acts like a spring. Recall Hooke's law from physics that says that the force needed to move this spring depends on 2 things. It depends on K, the force constant, in other words, how stiff the spring is, and X, how far you are moving the spring, what's the displacement. If we take this simple equation and we substitute in some variables relevant to atoms and we do some rearrangement, we get this new equation. It looks scary, but it's actually not that bad. What this equation tells us is that this variable called nu bar, also known as the wave number of light that the bond will absorb, depends on 2 things. It depends on Kf, again, our force constant. It's how strong our bond is. The stronger the bond, the more stiff the bond. As you can see, as Kf gets larger, the wave number must also get larger. Second, our wave number depends on the mass of the atoms. As you can see, as our masses get larger, the denominator of this fraction gets bigger. As the denominator of this fraction gets larger, the right side has to get smaller. Hopefully that makes sense to you mathematically. Heavier atoms result in a lower wave number. In summary, this equation tells us that the wave number of light that is absorbed by a bond depends on the strength of the bond and on the mass of the atoms in that bond. It turns out that the type of light these bonds absorb is infrared light. By shining infrared light onto a molecule, we can see what wave numbers of light are absorbed by the bonds in that molecule. Here are some examples. On the left, I have a series of bonds, and on the right, I have the wave number values of the light that is absorbed by each particular bond. Let's compare these first 2, CH and CD. D stands for deuterium. Deuterium is a hydrogen atom that contains 1 proton and 1 neutron in the nucleus. That means it is heavier than a normal hydrogen atom. How does the wave number of light that these bonds absorb compare to each other? As we can see, The carbon-deuterium bond absorbs at a lower wave number than the carbon-hydrogen bond. That matches what we saw for the equation here. We know that heavier atoms result in a lower wave number. Now let's compare these last three: carbon-carbon single bond, carbon-carbon double bond, and carbon-carbon triple bond. We see that these bonds also do not have the same wave number absorption value. Why is that? Let us look at bond strengths. If we look at the carbon-carbon bond strengths, we see that as we go from a single bond to a double bond to a triple bond, it takes more energy to break that bond. In other words, our bond becomes stronger. Based on the equation we discussed on the previous slide, stronger bonds should absorb at higher wave numbers. And we see that is true. A carbon-carbon triple bond absorbs at a higher wave number than a carbon-carbon double bond, which absorbs at a higher wave number than a carbon-carbon single bond. The payoff here is that because infrared spectroscopy allows us to see what kinds of covalent bonds are present within a molecule, it allows us to determine what kinds of functional groups are present in the molecule. For example, if you look at this table, if my infrared spectrum has an absorbance at 2200 wave numbers, that means I know I have a C-C triple bond in my molecule. I have an alkyne. We will talk more about common absorbances and how we can use them in structure determination in the next webcast. But for now, we have reached the end of this webcast. To recap, infrared spectroscopy allows us to identify functional groups present in a compound. The reason we can use infrared spectroscopy to do this is because each type of covalent bond in a molecule absorbs a particular wave number of light, and we can see that wave number by what is absorbed in an infrared spectrum. The presence or absence of an absorbance in an infrared spectrum can confirm or disprove the presence of a functional group. Of course, there are exceptions and we will discuss them in the next webcast, but for now, if an infrared spectrum contains an absorbance for a particular bond, that means the molecule has that type of bond. If an infrared spectrum does not contain an absorbance for a particular type of bond, that means the molecule does not contain that type of bond.